Alrighty, so um, here back at it again, quantum mechanics part 3. We might not cover everything in this section in one go. In that case, I might have to put this in pieces, but we'll have to see. Because I did try recording this earlier, the mic did not work. But enough of that. We better get going. So let's hop to it. So, continuous quantum mechanics. We'll cover the uncertainty. Let me get out of there. We'll cover the uncertainty principle, the wave functions, and hopefully the Fourier transform, which might actually be optional, but I'm going to cover it because I think it's somewhat helpful. It's interesting, but it might be confusing. So don't. If like the rest of this video is too confusing, don't worry about Fourier transforms. But anyway, we're burning daylight. Anyway, so continuous mechanics. The very first thought you might be looking at this is, what does continuous quantum mechanics mean? Well, this refers to systems where there is a continuous amount of, say, energy or momentum. And I better write this down here. But for example, discrete, which is what we studied last time, has to do with like bound systems usually. Normally, like the atomic orbitals of an atom are bound, and so they're discrete. This obviously isn't always the case, but that's usually a good rule of thumb, is that something like a bound system, like bound energy, is discrete. Continuous has to do with free systems. For example, like an electron that's coming in to Earth from the sun. It's a free particle. It's not bound to an atom, so it obeys the continuous side of quantum mechanics, as opposed to the discrete mode. Or, say, a photon usually is not bound to an atom, so it has no limit on how much energy it can have, as opposed to an electron inside the atom. But we're not going to worry about that too much. Point is, discrete and continuous mechanics are both pieces of quantum. They're like different sides or aspects of classical quantum mechanics. Note, I'm not going to do relativistic quantum field theory or anything yet, because that's a little bit more dense than this stuff. And it's going to be too confusing. Anyway, discrete and continuous is where we'll stop. But we better keep going. So, continuous. Now we better get going on. So, Heisenberg. Oh, forgive my handwriting. Heisenberg uncertainty. So, it's represented by this equation, which is hopefully not too bad. Greater than or equal to h power 2. This equation is not so bad. Hang on. As a note, x is related to space, and p here is related to momentum, and this big triangle shape is related to change. And so what does this mean? Well, what this means is that this delta p, which is the uncertainty and the momentum, because there might be like a range of possible momentum values, and there might be a range of possible space values, and when you multiply them, they have to be greater than this value here, h bar over 2. And I'm going to give an example where this might be somewhat easier to comprehend. Suppose that we have like that's not very good. Suppose we have like an electron, and let's say that it's bounded by a photon coming in from all directions. So we're trying to like restrain the electron with these photons. Because if you remember about last time, we talked about how photons can move or push electrons, and so we'll pretend like we're trying to restrain or contain or confine an electron to some point, which we will call delta x, which is the maximum. It's like the little space that we've confined the electron to. Well, all this means is that when delta x, the space uncertainty, is going like really small, the delta p, the momentum values, can range quite a bit. Note this does not mean that momentum equals all values. It's just that if we had like if we had some sort of machine that could measure the momentum of the particle, it could take on a wide array of values, as opposed when the space options are small. And it goes the other way. Like if we have some device that can measure the momentum very well, it's going to be very poor at measuring the location of the particle. And it might sound weird at first. There's probably loads of examples you can find on the internet. But I better stop here before this video takes like all day. Point is that in Heisenberg's uncertainty, the momentum and the space uncertainties have continuous values. So instead of just being 1, 2, 3, they can be like 1.5, 1.75, 1 in a million, and so on. This is why it's under this bit. And the next bit is wave functions. So, you might remember from the double slit experiment that sometimes particles can act like particles, and sometimes they can act like waves. In order to capture this, we have the theory of wave functions, where instead of representing the particle as a point, we represent it as like a wave, or like a height map, where the height of the map is loosely correlated to the probability of finding the particle. So, as an example, let's say that we have the sun here, and let's say that I better choose a better color. Let's say that we have the earth here, and let's say that we have like a proton. This proton can most likely be found near the sun, and it's less likely to be found near the earth. I'm gonna bear labels these bad signs. Gotta label your elements. Yeah. Sorry for that. Anyway, point is this particle could be anywhere between the earth if we were to go hunt it down and find it. Like if we have some machine that can locate the proton, and or represent it, we use a wave map. So this value, we'll call it psi, which by the way is spelled in English like this. not psi, psi, like of Poseidon. And it's used very often in quantum mechanics, which is why I'm using it here. And trust me, you'll see it a lot more in the future. Anyway, that is psi, and this value will be x, where x is equal to space. Well, if we want to know where we're likely to find the proton, we can draw it here. And it might, hang on, it might look a little bit like this. And all this means is that you're more likely to find the particle somewhere over here near the sun, and you're less likely to find the proton over near the Earth. But it's a non-zero chance. There's always a non-zero chance that it might leave the sun and travel to the Earth. And so we'll find it there at the Earth instead of at the sun. And as a side note, this will come up later when I go over some use of calculus in this quantum. But if we want to find the probability of finding it between two spaces, it's somewhat connected to the area underneath. In particular, we take the integral from x1 and x2 and take a value of psi times psi. I better remove that to not be confusing. Technically, there's more steps to this, but I'm not going over them. Anyway, the point is that if we integrate over this wave function, it will give us the probability of finding the particle there. T. So, like, if, for example, the wave function did not look like this, like if it was like this value, then this integral would be much higher. Whereas, if we're taking, say, the integral from here to here, it's going to be very little, which means that the probability is close to zero over there, and at least with respect to the rest of the wave function. This isn't necessarily that dense of a concept, but it is a bit weird to some people, mostly because some people on the internet will over dramatize. But I won't go into this. All you need to know is treat psi as like where the particle is most likely to be, more or less, and you'll be ready. That's all you need to know about wave functions, essentially, is that they represent where the particle could be as a wave rather than as a point. Now we're on to the final stage of this, at least for a moment. Now, if you hate abstract concepts, back away. Otherwise, stick around. As a warning, though, this will get quite abstract. So, the last section, we learned that we can represent particles as waves. Now, one thing you can do with waves is you can add them together. So let's say that we have a wave that we call phi1, and it's equal to something like this. Now we'll have another wave, go phi, that does not look right, 2, which we'll say is equal to some other wave. Well, we can take something called a linear combination and this will come up later when I go into linear algebra inside of quantum mechanics. But if we have a wave that's like psi, it can be equal to phi 1 plus phi 2. Or in other, better demonstrate this with a picture, hang on, I'm going to just put it off to the side. It might look a little bit like this. You might know this if you've ever been in a band. You can have like this phi 1 could be like a tuba's wave, and this phi 2 could be a flute. Oh, that is not very well written. Well then, this value here could be like the orchestra. The orchestra's wave will be a combination of all the possible instruments. I haven't listed a whole lot here. There's only 2. But obviously, if you have like an array of instruments, then you just add up all the waves together. And that's like the idea of the Fourier transform is that you can get to any orchestra wave by adding up all the waves of all the instruments together. And we're going to like a slightly more interesting version of this as regards quantum mechanics, which we shall call something different. So let's say that we want to mathematically create a wave that looks a little bit like this. Just a spike. So not like this, just a singular spike. Well, in order to approach this, we actually have to add a bunch of different waves. So we can have like a phi plus phi plus phi plus phi plus phi plus and on and on. And by the way, the number of this will actually approach infinity. Once we have an infinite number of phis, then they will all add up to this wave function that we have right here, which is this thing. Technically, you're supposed to. This is where calculus comes into play, because calculus lets you add up over a bunch of infinite values, which I'll get into in a while. But basically, you can stack an infinite number of these phi waves to get a singular spike. And, well, what does this have to do with quantum mechanics? Well, not much if it's going too simple, but this plays into the momentum uncertainty. Because remember, like delta x times delta p is greater than or equal to h bar over 2. And you might also remember that we can represent quantum particles as like waves. Well, we can actually combine these ideas into one. Let's say that we have a certain wave, which we will call phi. You might say I'm using lots of phis. There's a reason for that, but I won't get into that in a minute. And in respect to k, let's say that this has something to do with the momentum. We shall also have another one call it psi with respect to x. Let's say this has a lot to do with delta x. Now, one way you can think of the momentum uncertainty is like a wave. So if the momentum uncertainty is like this, you can add up a whole bunch of different waves together, you know. Like the momentum wave is not very well constructed. You know, it might look like this. Well, then the position wave would look a little bit like this, or more like this, anyway. And you can see how these go together. Technically, the proper way of writing this is that sigma of like phi times like sigma of psi must be greater than or equal to h bar over 2. And for instance, this value is loosely related to how this value here, hang on, I better use a different color. This value is basically how spread out the function is. You know, like as you can see here, the sigma psi is equal to not a very big number, and so this value is not spread out. This is different as opposed to sigma of phi, because I can see phi is very much spread out, and so sigma phi is going to be a huge number because it's spread out, and sigma psi is going to be a small number because it's not spread out. And this is how we like combine, you know, these two ideas into one with the Fourier transform. It's just that instead of using numbers to explore quantum values like momentum, we use waves and wave functions. And that's it for now. Hang on. And I know this might seem like it's fast, but the reason I want to make it fast is I don't want the mic to die out. That's a quick warning. Hang on. Anyway, so this is nearing the end of our ultra simplified quantum mechanics. Obviously, I'm not going super gnarly. I'm honestly pretty light as far as this goes. I've gone like the speedrun route and the super simple route, but some of the stuff from here on out will get a little bit more mathy. But don't worry, I'm going to introduce a couple of videos which should hopefully make the math really easy to understand. And I'll also explain exactly how the math is used. You know, I'm going to make one about linear algebra, and then I'm going to explain why linear algebra is in quantum mechanics. I'm going to make one about calculus. And you did see a teaser with wave function probabilities, but calculus has a role in quantum mechanics as well. In fact, it has a very important role, but instead of just glossing over it, I'm going to actually give a hopefully somewhat understandable application of calculus in quantum mechanics. Just be warned. Don't worry, I'm going to find a way to make it easy to understand. You'll probably even think that you're a pro at linear algebra, but even though you might not be, but you know, you'll feel confident enough to understand this. And well, that's honestly all for now. Better end the video before my mic has an issue, and see you next time.